that you don't have a mic, so I'll make sure that I look at the chat section in case you have any questions. And if you have any questions or any comments along the way, feel free to uh, shout out or send text messages, and we'll try to stop at that point and cover those questions as we run through it.
And we do have some places for audience participation, so
yes,
we will see how that works, because I just realized that I can't type well in the slideshow mode. So it may not work the way I intended it, but we'll see.
Yeah. Well, what I can do is I can actually type. Oh, now how that would because I can type on mine actually, and just at least I can record it, and
okay,
and then we can add it on the end or whatever as we.
Yeah.
Okay.
So welcome to Engineering in the Modeling Classroom. Kathy and I both have had experience designing biology units with engineering problems, engineering scenarios involved, and we're both very familiar with the engineering practices. Kathy, do you want to?
Yeah, and I always used engineering projects in my classes in physics also when I was still teaching. And after I started really doing a deep dive and working with actual engineering educators, I learned all the things I was doing incorrect. So it's always a nice thing to find out later. But yeah, so hopefully we'll have a nice conversation tonight.
And please feel free to jump in, ask questions if we're not making ourselves clear. And like I said, there's definitely points for audience participation that we're going to stop and pause for, and also for some discussion, because inserting engineering into the science classroom is new in general, let alone into the modeling classroom. So, good. Nothing's working well today. Oh, there it is. Okay, I got it now. Okay.
Okay. So one of the things we want to talk about was basically, why should we include engineering practices in our science classroom? We all know that there's educational policy changes within GSS calling for incorporating engineering into the K-12 classroom, and that's all well and good. But there's also been some studies in case some parents ask about it or administrators ask about it. I know I always like to have a little bit of data to support why I do anything in the classroom besides just saying that the NGSS says I should do it, or the standards say I should do it. And that's really, those improved learning ideas. For example, increases in conceptual gains, scientific reasoning skills, mathematical understanding. And the numbers next to it are references, and those references are down at the very end of the slideshow in case you want them. And actually, if you want any of those articles, feel free to, email me, and I'd be happy to, get them to you. But yeah, so we've seen many conceptual gains, especially in the biology classroom when we've been using engineering applications to drive those units. Does anybody have questions about any of this?
And we've also noticed increased science engagement as well. Kathy, do you want to talk a little more about that, or?
Are much more fascinated with science, with those units that use engineering, because it makes it very interactive and real world for them.
Okay. So just to compare and contrast the difference between engineering and science, this is a very simplified version of the differences, and it basically boils down to this. Engineers solve problems. That's their goal. That's not the only thing they do, but that is their driving force, so to speak. And you can think of scientists as asking questions to discover something about the phenomenon that's out there in the world. And again, very simplified, but to give some examples. So a biology example is that how an engineer would approach a problem is children with cystic fibrosis often die in their 20s. And so an engineer would be asking, what solution can we design to decrease the mortality? Whereas a scientist, when confronted with with children with cystic fibrosis, would go, okay, we know they have a defective gene. How does this defect cause cystic fibrosis, and what does that tell us about normal bodily functioning? And Kathy, you want to do the physics example?
Yeah, in physics, actually, we have a Department of Engineering Education here at OSU, and one of their engineering problems is you have to design some type of amusement park ride or some type of operation. In this case, I used an example of that's been used in secondary education about designing a roller coaster prototype that contains two loops, requires energy input only once during the ride, and so forth. So engineers really aren't too concerned about things like, friction and how that might actually affect my elastic potential energy going up, and what the relationship is between specifically friction and energy loss. Now, the engineers do necessarily need to know something about friction, but that's not really their main focus. And one of the things I, always like to talk about is the fact that, engineers, if you ever watch them in the engineering lab, don't necessarily control variables. So they'll change like a couple things at a time, whereas my science mind is saying, oh, no, wait a second, you don't know which one really actually affects this. Why are we doing it this way? But that's one of the main differences between engineers and scientists. Engineers, for the most part, really aren't concerned too much about control variables. They just want a solution that actually works and benefits whoever the provider is that they're trying to actually give the solution to.
And so if we look at what NGSS says about engineering versus scientific practice, so there are 8 scientific practices, 8 engineering practices. There is overlap between the two, and I'm going to just run through a side-by-side contrast, and then I'm going to go through how engineering practices would be applied in a sample engineering problem. So the very first one, scientific practices, is for NGSS is that scientific practice is to ask questions. For engineering practices, it's defining a problem, and you'll get a little sense of what that looks like in just a few minutes. Scientists develop and use models, and engineers build and use models. It's a little bit different. So scientists are trying to develop a model that captures their understanding of a phenomenon, whereas engineers build models that, yes, it captures their understanding of the phenomenon, but it does more than that. It allows them to test their solutions and to see what's happening with something and with a solution. And so I use the word build instead of develop there because it's more applicable to what they're doing. Scientists plan and carry out an investigation, and this is where Kathy's talking about the controlled variables piece, I think, that comes in. It's very important as scientists for us to control those variables because we need to know which of those things is responsible for any effect we see. Whereas engineers investigate how to fix or improve the functioning of a solution or technological system. And so, as Kathy said, they don't really care. They just want to know, okay, so this, and this is not working right. I've got to fix all of those. Scientists and engineers both analyze and interpret data, but engineers tend to focus on how well a solution functions. So they tend to collect the data about how well the solution is functioning, and they're analyzing and interpreting it with that lens in mind. Both groups use mathematics and computational thinking. Oftentimes, scientists are using them to represent a model of a phenomenon or explain a relationship in a phenomenon that they're observing, whereas engineers often use applied mathematics and computational thinking. So in order to work out the parameters of their design or something like that, Scientists construct an explanation from what they are doing. Engineers design a solution to a problem. Scientists engage in argument, and so do engineers, both from evidence, but scientists tend to use this to defend an explanation of a phenomenon, whereas engineers might use it to advocate for a proposed design. And they both obtain, evaluate, and communicate information, although their audiences are often different. Kathy, do you have anything to add to this?
No, I think you did a great job. Does anybody have questions?
Yeah, that was my next. Somebody said something, but I can't hear it. Was that correct?
I don't know. I didn't hear anything.
Okay. So if we don't hear you, just type it in, and Kathy's monitoring the text thing, and we'll stop and try and deal with it. So because we have people here from all disciplines and all grade levels, I thought I would share an example of engineering design practices applied to something we might be all familiar with, which is curriculum design. So here's the situation. Your science coordinator has evaluated data from the end-of-year testing and noticed that 9th grade students' graph interpretation skills in the district are lagging behind state scores. She is concerned because these skills are necessary for future success in science. She charges you to lead a team to design a solution to bring all students up to proficient level within 2 years. So I'm going to try and go over to the thing. So if you were going to define the problem, you would have to identify who, what, who is affected, what the problem is, and why it needs a solution. And you would also include criteria in this. And I'm going to switch back to the defining the problem space, because otherwise you won't be able to do this. And I'm going to ask for your participation at this point. So, and I might be able to actually write. We'll see. But Kathy's going to type. So does anybody want to figure this, to decide on the population that you're designing this problem for, or is affected?
Can you repeat the question, Anita?
Yeah, so who is our who? Who do we need to design this for?
This is Carl Englert. It seems like just 9th grade students or younger students would be your population that you care about.
Okay, so we're going to say 9th grade students.
And younger students, I think, too.
Yes, okay, because you're saying that they might be affected before. Kathy, are you typing that?
Yes,
in
typing
it. Okay, because I can't do it. So 9th grade students and younger students. So 9th grade and younger students. Okay, and what is the what?
It sounds like the students don't have reasonable graphing or interpretation or mathematical analysis skills.
So 9th grade students need to improve their graphical analysis skills or graphical interpretation skills. 9th grade and younger students need to improve their graphical analysis and interpretation skills.
It seems like it based on your question.
Okay.
Or your data.
scenario. And yeah, that's all you got right here. So, and what's the why? Anybody can go, but you can continue, Carl,
Oh,
if you want, or you can pass it
well,
off to.
I'm thinking about the why. It's unclear to me. There are so many options at this point. You have, like in my school district, we have an influx of lots of new ELL students, and those folks get added to the general scores. So it's hard for us to like have a normalized group of students to decide, oh, this is the change that's happening in the schools, or this is what's different about our curricula and how we're affecting students. I have a hard time making
So this
sense
is
of
the
those things.
slight difference between engineers and scientists. And this is going to sound really callous, but at this point, the engineers don't really care about all of that. What they care about is, given their scenario in front of them, why do we care about this? Like, why is this important?
Oh, I'm sorry. So what you're saying is I'm taking it more from a scientist perspective of why is this happening? And from the
Right.
engineering perspective, I could look at this of, well, how do I just solve this problem? What
Well,
can I
not
throw
the
at
how
this?
yet, but like, why should we solve this problem?
Oh, because students need to have good graphical analysis skills to make sense of all the data they're going to see as they get older.
There you go. Yeah, exactly. Kathy, you've got
At least
that?
that's one reason. I
Yeah.
suppose.
I'm trying to get it. Yeah.
Necessary for future success in science. You may have to repeat that for Kathy.
Uh, So students are going to see lots of graphs in their future life, even outside of science and engineering classes, and we want to be the people that help the students make sense of that information and understand what's meaningful and not. And so we'd love for students to be able to have those skills of analyzing graphs to help them make sense of things and make decisions in their lives, even after they get done with school.
Kathy, do you have that in a nice condensed version?
More or less, more or less.
Whatever you do. Okay, I'll let you read it back in a second. Okay, and the very last thing that engineers put into their problem statement is they put in the criteria for success. So these are usually embedded in the scenario that they've been given. And they can change later, but what are criteria for success that are in there?
Can I keep going?
You can if nobody else has interrupted you.
Excellent.
But people are free to interrupt.
I would say if this was me, I would say, okay, my criteria for success would be that I see a 10% improvement in students' results per year.
So what does your
might be too-
science coordinator give you as the criteria for success? Can you see the screen? It's in the last sentence.
Yeah, I'm looking. I need to reread it.
Somebody else could help
I
you
see.
out.
I suppose the goal would be that my district gets to the point where we're at least even with state scores.
Okay. And your science coordinator has been even more rigorous. She wants all students to proficient level within 2 years.
Mm-hmm.
She's got a pretty high standard.
Okay.
So she definitely wants them up, but she wants them more than up. Probably her job's on the line. Okay. So Kathy, when you're done with that, you're going to read that back to us, and then we're going to, I'll show you what I came up with too.
Yeah, so the who for Carl was ninth grade and younger students. What was need to improve their graphical and mathematical analysis skills. And for the why, from a scientist perspective, because of the influx of ELL students, so they get added to the scores, and it's hard to make sense of what's going on. So it's hard to make a sense of a controlled experiment there. And from the engineer's perspective, because the kids need good graphical skills for future success, because they will see lots of graphs in their future, and this will help them to make sense of this information to make decisions in their future life. And the criteria for success is that the district supervisor wants everybody to be at proficient level, all of the students within 2 years.
And so, very similar, and it was supposed to be color-coded when we put the formatting on it, changed it, but very, very similar to what Carl came up with. They need to interpret graphs at the proficient level because graph interpretation skills are necessary for future success in science. And Carl actually expanded that out and said, you know, hey, we need this for life. I mean, this is something that's important. And so that's where engineers start. They start with this problem statement and they define it in this way because then it allows them to figure out, okay, how do I start to grapple with this problem? And the very first thing that they do, and this one I'm going to switch to escape from the presentation so I can type. The next thing they do is define the problem with resources and constraints. And Kathy, I'm going to ask you to use a classroom discourse management technique and to call each person out one at a time and ask them to come up with either a resource or constraint.
Okay.
That,
So
but we probably ought to define resources and constraints before we continue.
Okay. So
go ahead.
Yeah, go ahead. No, you go ahead.
Oh, thank you. So a resource is something that you could use to help you, that will help with the problem. That's something that's available, which could be, you know, could be anything, could be teachers, could be, you know, whatever you've got that will help solve this problem. And a constraint is something that is going to limit the solutions to the problem. Could be lack of training of teachers. So I will put, you know, teachers is a resource, and lack of training. So those are our first ones. And Kathy, can you go around and get everybody to kind of give us one?
So yeah, so what I'll do is I'll just start off down the list. Belinda, how you doing tonight?
I'm good, Kathy. How are you?
I'm doing fine. So
Good.
what resource or constraint would you like to add to this? Do we have? What resources do we have?
I think as a teacher, the big one is always time. You know, how much time do you have in the classroom?
That's a constraint or a
Yeah,
resource?
the constraint. A resource might be, you know, computer graphing technology.
Okay. And Celeste, what about you?
Is Celeste typing in, Kathy, or is
Um,
who else?
Yep, I am. She is typing in.
Okay, good. I couldn't see it.
I'm waiting for her to type up. Yes, sorry. Yes. So I'm not really managing very good student discourse because I'm going straight down the line. So y'all know exactly who's coming up next, which is a very poor strategy. But okay, so lack of training. So Celeste says her first thought would be lack of training.
Oh, okay, which is already up there.
A constraint.
Pardon? That was yeah.
That's a constraint, correct, Celeste? Okay. Yeah, actually, it should be a constraint, shouldn't it? I don't know why I haven't asked that question. All right, Earl. What about you? Resource constraint? Got some ideas?
The constraint is that maybe there are students that are not enrolled in a course where they do graphing. So it depends on the curriculum. And so the resource is maybe to align the curriculum so that students are engaged with the graphing problems.
Did I summarize that okay, Earl? I was.
Close enough.
Okay.
All right, excellent. And what about you, Carl?
I think I'll add for a resource, the idea that you could look at research into best practices of education and engineering and science. And for constraints, I struggle as far as the as far as the question or problem that we have been working on. I struggle with uh, the fact that each group of students isn't the same, so there's no control group. That's a constraint for
The
making sense
variability among
of
students.
results. The variability of students and human research results.
Okay. So yes, an applicability of the research when you have variability.
Mm-hmm. Mm-hmm.
Okay. Kathy, how many people do we have signed up, and how many people?
We have
Okay.
four more. And James,
Four
what
more.
about
That's reasonable. We can do that. Go ahead.
you? James has a resource of, it's in the chat box, teacher supplements to your current textbook. And then the constraint would be money to spend on additional resources. Oh, that's a good one.
Yeah, money. Money's always a good one. Oh, the other way around.
Yeah,
That's
because
it.
usually they're probably going to want you to do this for no money, no extra money.
So this is lack of money as a constraint,
Lack of
right?
money. Yeah,
Additional money.
additional funding.
Yeah.
And Lenny, what about you? Yeah, we might have missed.
That's okay.
Yeah, so we'll go with Lynn. What about Lynn? Okay, Lynn says simulations for graphing.
And that's a resource, I'm assuming?
Resource, yeah, and then she said also thinking of lack of money as a constraint. So, so thinking about those same ideas. And Megan, what about you?
Okay, can you hear me?
I can
Yes.
hear you, Megan.
Awesome. So I was going to say creativity is a resource. I don't know if that kind of falls in that.
I like that.
Mhm.
And in terms of constraints, since it's a district-wide mission or mandate, I think that sometimes what I face is that teachers have either a reluctance or fear or unwillingness to kind of reach out of what they've been doing in the past and, kind of not put all of the blame on the students, that they have to, maybe kind of try something new. And I don't know how to say that more quickly.
Resistance to change work.
Yeah.
Okay. Did anybody else come with another idea along the way as everybody else was talking that they'd like to share? Oh, Lenny said that we can use FET and shore door sites for many graphing activities. So there's lots of um, specific
There's lots
sites.
of online graphing resources.
Yep.
Okay. So you can see how this works, that by working in a team, and engineers often work in teams, you can come up with this list of resources which will help you design a solution to the problem. And the constraints, which it's not that they stop you from designing a solution, but you need to figure out how do you work around these, how do you accommodate these, because you can't design a solution that is not going to work in a district, because of lack of training. If that's the problem, then you're going to have to, your solution is going to have to include a way to accommodate that. And so that's why it's so important for engineers to get their resources and constraints down pretty early on, so that when they go to start designing solutions, they can start to look at their solutions against these resources and constraints, and that influences their design. So going back to this. Okay, so the next thing that comes up is then they might do some investigations about how to fix. And we've already come up with some kinds of investigations. One person said, but let's go to the literature. Let's go and see what the literature says about best practices that we could use. Another one might be, let's have a look at these simulations and see which are useful. Another one might be to interview students as they're solving graphing problems and see where they're having difficulties or analyzing graphs. Does anybody have any others they'd like to contribute as possible investigations?
This is Carl again. It might be worthwhile to look at teachers or classrooms or schools that are doing much better than the other schools in the district, and see if there's something that they're doing that the other schools aren't doing to help with this issue.
Yeah, exactly. So going to find model solutions that could be used, and examining them for shortcomings and for things that you do want to be able to do. Other thoughts? Okay. So there's lots of different ways that you could think about how to fix it. And then the next thing, once you've got kind of a sense of the background, like Carl said, from going to look at other schools, or from looking at the research that's been done on graphing, or from interviewing students at your school as they, analyze problems, talking to teachers, then the next step is to brainstorm solutions. And so the basic rule for brainstorming is that anything goes. So it doesn't matter what you come up with, it all goes on the table and it all gets written out. And it's kind of fun to watch kids in action with this. Kathy, do you agree? Because it's very hard for them to resist analyzing and critiquing the solutions. But on the other hand, they can sometimes be super creative. So
Yes. Yeah.
So it's a very fun space to watch kids be in. And the next step you would take would be to evaluate these solutions against the resources and constraints and identify likely candidates. So once everything's listed, and then you go back and do that evaluation step and look at them and say, okay, so, well, it would be great if every kid could have their own computer and they could, we had access to this graphing software, and we could use online data to do this, but honestly, we don't have the money for it. So, that kind of thing. And then you kind of go through and figure out which ones are the most likely candidates. And at this stage, there's probably a few. And then each person in the group probably has their own favorite out of those ones that are likely. And this is where engaging in argument from evidence, that practice becomes salient. So thinking about what affordances and constraints are offered by each solution. And affordances are slightly different than resources. Affordances are what each solution would provide. How does each solution help you get to solving the problem? And the constraints are really pretty much the same constraints as listed before, but sometimes a solution actually imposes its own constraints. So for example, the computer one I just proposed, one of the constraints is that each kid would have to have its own computer, his or her own computer. They're not it. And then have to go back and think about, well, which solution is likely to meet the established criteria. It's not that you know, but that there should be able to be some, based on your research, based on what you've done, you should be able to figure out which ones can meet the criteria. And so an argument kind of ensues, a very respectful argument and based in evidence, but a slightly different evidence-based, I would suggest, than what scientists would engage in. Kathy, do you have something to add to this?
No.
Okay.
No,
You sounded doubtful.
oh, sorry, I was typing. I was chatting on the chat window.
Do I need to pause to allow people to?
Yeah, some people might have some possible brainstorming solutions they would like to suggest.
Oh, okay. Is that what happened? Okay, I didn't allow space for that because I was worried about time.
Well, we can see if anybody has one. I mean, one comes to mind very quickly to me when I think about that, about a possible solution.
Okay, go ahead. Kathy wants to put in her solutions. Go ahead.
Oh, no, I wanted to see if someone else would come up with it too, you know.
Okay, so go ahead. Open it up and see if anybody's got any solutions.
Yeah, because the first one that comes to my mind is, of course, modeling instruction, right? We're all here from AMTA, and you might have actually said that already. I don't know.
No, I didn't actually.
Oh.
I didn't. You know, just because I was thinking everybody's thinking that, yes.
Okay, so I will throw my hat in the ring.
Okay.
You know, this kind of brought to my attention the idea of the tug K or something similar, and the fact that doing diagnostics with the kids to figure out where students are at, so that you can either group accordingly or think of what resources would best target certain graphing issues, whether it's the kids who they don't even know how to scale the axis of their graph versus the kid who's really ready to kind of address the idea of something like how does slope intercept form apply to a linear relationship.
Did I capture that? Sorry. Did I capture that okay?
Yeah, totally.
Okay, good. I always verify back because sometimes, as I'm trying to process and write, it doesn't always come out the way I intend. I have one, having students build graphs instead of just read graphs or that they're given. Having students actually do the work of constructing graphs and then having a conversation, which is what we do in modeling instruction in general, but having a conversation about what that graph is communicating. So it's sorry about that, everybody. You may hear that again. I do not know how to turn that off and keep everything else going on my computer. So building graphs, constructing graphs, and deciding as a group what the best representation is for the need. For the communication need. It's kind of a so is there anything anybody else would like to add?
Peer evaluation of graphs.
Yeah, that's an excellent one. Yeah, Megan mentioned ranking tasks are great for improving graphing skills too.
So incorporating ranking tasks into the curriculum.
Right.
Another thing you might be able to do if this was important for the whole school is to have math teachers and science teachers together work and collaborate on developing uh, a collaborative curricula that they'd work across their science and math courses together to address this issue.
Mm-hmm.
I like that one. Cross-disciplinary
Yeah.
initiatives are a favorite of mine. But I'm a little biased though, so.
Me too.
Yeah, and Megan mentioned, if everybody's looking at the chat, mentioned that she likes to teach math-phobic kids how to solve, predict using graphs as a substitute for algebraic problem solving. Many I'm bad at math students open up when they realize this is an option. And yeah, I totally agree.
Yeah.
You know, I've seen kids who refuse to use mathematic or algebraic problem solving and try graphs always, like because they you know make sense to them.
2 problems.
Yeah.
There we go.
All right. So now, moving on. I think we need to move on to the 742.
I know. I was like, okay, okay, yeah.
Also many great ideas.
I know, isn't that great? Now we've got them all down here too. So, and then an engineer would go and design a model curriculum, or a group of engineers would design a model curriculum and implement this in a few classrooms. And once they had done that, they would collect data on how well that was working, using some, in this case, assessment or several assessments. And you know, one example is that they already have the year-end test scores, so they can analyze and interpret year-end test scores, and they can evaluate how well the solution meets the criteria. And I have this word. You remember the criteria was all students will reach proficient level at the in 2 years. And I have, I deliberately made it all students, even though I know that's unrealistic. One, because that's sometimes what sometimes seems to be the pressure that is put on. It's like everybody has from further higher up. So, and it allows me to introduce this engineering term that I really love, which is called satisficing. And it basically means that no solution is going to be perfect. No solution is going to meet all the criteria, fit within the constraints that are there, and the resources that are provided. And sometimes, so basically, you're not looking to come up with a perfect solution. You're looking to come up with solutions that satisfice. They kind of fit that nice juxtaposition of maximizing the outcomes and getting as close as possible to those criteria, and still taking maximum advantage of the resources, and minimizing the effect of the constraints. And I love this term because it's one that I kind of have started using in my everyday life. So, so I really like it. And then they revise the solution and repeat. And this iteration piece is also a really important part of engineering practice, and something that I think is a real benefit for students to learn. Oh, we don't get it all the way right the first time, and so we go back through and we get a chance to revise, and we repeat and we try again. Kathy?
Yeah, I know that's one of the most important parts, and I think that's where I mentioned at the beginning where I let my students down when I was teaching physics is that we would do these engineering projects, and the revise the solution piece, I would maybe have them write maybe a paragraph or so saying, what would you do differently? But they never actually were able to work through that failure. So it's like, oh, well, that didn't work. Well, too bad. So long. We're going on. And never really got them to actually go back and revise that solution. And that's so important for engineers. It's like that's the essence of being an engineer, being able to revise your solutions and work through those failure problems and failure points at the end.
And then the last one I'm going to talk about is communicating information. So the information is always communicated out to somebody, whether it's a client in the terms of a report, and in this case it would probably be presenting the solutions and findings and recommendations to the school board and the community. Okay, so I'm going to pause just here. Does anybody have any questions or comments before we go further?
I do. This is Carl.
Yes.
And my question is, I do projects that are engineering projects. I mostly teach physics, and I use modeling pretty exclusively. And I am uncertain how to incorporate the project. I just visited a school a few weeks ago called High Tech High, and they seem to do all of their projects at the beginning of a unit. So like if you think of a unit that I might do a project in, like projectile motion, and all the kids make little catapults, and they go through this process that you've been talking about here, and they launch little balls, and they use calculations or whatever they use to aim and hit their targets. When does this project happen in the modeling curricula? Does it happen at the beginning?
Oh,
and
Carl,
so then they have a reason to do the project?
You set us up so nicely for our next part.
Yeah. Yeah, the only thing I'd wanted to add is that, this is the engineering design process that the kids are working through, and you don't necessarily have to tell them that, but what we just talked about were just all the steps in the engineering design process. But Carl set us up really greatly for the next slide.
Yes. So Carl's question is wonderful, because that is a concern. When do we put it in? How do we fit it in to the modeling curriculum? So these practices are, is just what they would go through, and you could do it in a number of different ways. And we're going to talk about this both in biology and physics. And sorry for you chemistry people, but Kathy and I are kind of sticking to our comfort zones. So, So there are three broad ways, and there are many other ways. We just chose three general outlines to integrate this. Kathy, did you want to do this piece?
Yeah. So these are the three ones that we've been playing around with. One's of course the capstone engineering project that maybe you do at the end of each unit, or the end of the year after the students do that. So like Carl was saying, you could, after the end of projectile motion, you give them the let's project whatever across the room kind of idea. And then of course the engineering project that drives a single unit and is integral to the unit, which is also what Carl talked about, was like the High Tech High, where the kids, you start off with this project, and it's a really cool way to start the unit, because then the kids, they can even start to design it and say, I don't know about this, I don't know about that. For example, if we go all the way back to the roller coaster idea, they might come up with, I don't know much about friction, I don't know about, et cetera. And that's an easy way to then outline the unit and say, this is what we need to go through. And then you can basically start off with your normal modeling unit and run through it. And as you go through it, then the kids can spend some time talking about their engineering design process, and then finally finish up that project. The other one is a year-long engineering project that drives the entire curriculum, or is an informed model that was developed, so that we can start off with something, for example, like in biology, where they might be talking about population control of maybe a deer population that was in the area. And as they go through each unit, how can my unit inform what's happening with my solution? So they may start off with looking at just population interactions of what's prey on the deer or whatever. And then as they move into evolution, they might come up with a new type of design solution that they could implement. So that actually makes the improved process a part of the year as you go along. These are a little bit harder, of course, to come up with those good ideas that drive it across the whole year. But those are my favorite personally. That's my favorite, the very last one.
Okay, so to give some examples of these and what they might look like in biology or in engineering, these are just examples, and then we're going to talk a little bit, and hopefully you will contribute about some of the advantages and disadvantages that you see to each approach, because my guess is that all of you have been kind of thinking about this, and that's why you're in this webinar and listening and participating. So for biology, an end of each unit project, you could have at the end of the inheritance unit. The zookeepers need to have a reliable plan for producing animals with rare traits so that people will want to come and see them. And based on their knowledge of genetics that they've just acquired, students have to design a breeding plan for one of the organisms at the zoo. And a nice way to build in iteration and revision in this type of unit is to have students start with a single trait and then realize, oh, if I had 2, 3, or 4 rare traits in a single organism, that would be a much more rare organism, and so then they would have to go back and redesign and use some of their more complex inheritance knowledge. They could also drive the model development within a single unit, and so for example, at the beginning of population growth and evolution, you could introduce the idea of an invasive species. And for Kathy and I, when we started in Pittsburgh, stink bugs were destroying crops. They are a lot, and they're moving north. And organic farmers need a solution that does not involve chemicals to control the pests so they don't lose money. And by getting them involved with this, they kind of have to figure out, well, how did the stink bugs get to be so big a population? So they have to explore population growth and figure out, can they control them that way? And then introducing the example of a predator, that one type of that predator or one variant will prey on them, on the stink bugs. Then it's like, okay, so how can we exert evolutionary pressure on the wasp population to favor those that will prey on the stink bugs? And then students get to explore those concepts within the unit, and they see the need for exploring each concept as they reach the limitations of their knowledge to design a good solution. And the year-long driving development of models, there's definitely the deer one. And another one that I like is because it's so pertinent, and there are actually real groups working on them at the universities, collaborative groups of engineers and scientists, is biofuels. So the idea that you need low-cost alternative fuel sources, and so you need to design or select or find a biofuel that and design a plan to grow this crop so it will be the most efficient biofuel while minimizing impact on the environment. And that gets at everything from energy flow to ecosystem interactions to evolution, population growth, inheritance, and it allows all of the topics within it that you would cover in biology in a year to come up as students work through their solution and find a need for the knowledge, and they get to apply each of those concepts that they developed, each of those models that they develop as they move throughout the year. And Kathy's going to do the same with physics. We didn't know who we would have, so we're doing both sets.
Yeah, and I'll just go through these really quickly because I'm looking at the time here. Yes, end of each unit, one of the examples that I know my kids were always enjoyed was the projectile launcher that we did with pumpkin launchers, so they could design something that would, shoot it across the football field. Pumpkin, any kind of gourd works. And have them look at that and try to talk about their future improvements. Now, one that drives the model development within a single unit, for example, like force interactions. If you start off with that wheeled vehicle that you might have already done before, or you might say, okay, well, what's going on here? And the kids could say, well, what do I need to know? And that would be friction and forces. And you'll see that there's actually something that's kind of interesting here, because when, for example, like Carl was saying, like these ones that go the whole year, could this wheeled vehicle actually go the whole year? Because you're also talking some energy ideas here that you could also use, right? And for example, the year-long one that I came up with was thinking about just you're hired to design that roller coaster, right, which we had mentioned before. And at this point, when you introduce it at the beginning of the year, have the kids decide, what kind of concepts do you need to know about in order to answer this question? How are you going to be able to design this? And they'll come up with all the different ideas having to do with mechanics and kinematics, and that we're going to be using throughout the year. And then we can actually move through that as we go. And they can constantly try to refer back to that roller coaster plan after every unit and work through that. But those are a couple examples. Any questions?
Oh, okay. Sorry. I just wanted to get to the idea that, and then we can take questions, but that all of these problems that we are proposing, or all of these engineering problems, kind of are wicked problems. And this is a term that engineers use to indicate a problem that's complex and multifaceted, that there's no one right pathway to a solution. And not only is there no one right pathway to a particular solution, but there are multiple solutions that can be correct. And again, this idea, the solutions may not achieve all of the criteria. You may have to balance resources and constraints with achieving criteria. And so there is not a perfect world, is with it. And I think it's important when working with students and trying to give them a real sense of what engineering is, that these problems are wicked, that they're not just going through the motions of just, oh, can I guess what you want me to do so that I get an A on this project, if that makes sense. So it's not, oh, if I follow this pathway and if I do things, all this, you want them to engage in the practices, and that's the pathway you want them to engage in. You want them to be able to be creative and to be able to come up with multiple different solutions and to have to engage in a genuine discussion with their classmates about why their solution is a good one. Go ahead, Kathy, and then we can take some questions.
No, you did a great job. So I guess that's the next slide.
Okay, I do have affordances and constraints of each approach. I wanted to know if people, I'm again looking at time, and what we could do is we could go on to the last slide and kind of wrap up and then come back to that, or like open it up and have it as part of the discussion.
Right, that's a good idea. So,
okay.
Yeah.
So, so the relationship of engineering to modeling instruction. Kathy, can you want to do the first one, and I'll do the last one?
Yeah, I mean, engineering, if you really think about it, is the ultimate model deployment. Since it's real world, especially the year-long projects. I mean, you're sharing these year-long. Ones allow the improvement to go on, as I've already said a couple of times. So it's really something that's integral, and I think it really, really meshes quite well between engineering and modeling in that sense. You want to do the second bullet?
Yeah. And the other thing is that a lot of the engineering, not all of them, but a lot of them reinforce modeling practices. And an example is this evaluating and revising. So they're evaluating solutions and revising their solutions, but when we are developing models, and we need to evaluate the models and have students revise these models. So this practice, this iterative practice, this idea of iterative practice, that it's not a one and done, I think is something that the more reinforcement students get in that, the better. And also the multiple solutions kind of idea too, I think is really important and goes nicely with modeling. Because there are often multiple solutions to a problem using different representational tools, and I think it's nice that students get to experience that in a real world place too. So comments and discussion, and this can include discussion on what the affordances and constraints are on the different different models we gave you, different ways of putting engineering into the modeling classroom.
Yeah, so Belinda said in the chat menu that she thinks modeling can enhance the engineering design process by helping to make student thinking visible.
Yeah.
Yeah, which is a really good affordance of any of the engineering types, whether it's a capstone, integral unit to the unit, or a year-long project. So there's no comments or questions.
I have a comment. This is
okay, yeah.
Sorry. This is Carl. My comment or question is, when I do processes like this, it seems like I really enjoy the brainstorming part initially, but then once the process begins and I've got four physics classes, it seems like the students watch each other and then they look and see what they think is best that's going on in other parts of the classroom. And then they, instead of having a wide range of engineering projects and multiple ways in which a problem becomes solved, I only have a few because of that sort of copying of other people's designs. And I struggle with that because the students see, project or engineering project after engineering project, who seems to do really well on them. And then other kids are just they seem to like to wait until they see what, Joe's project is like. And then they do theirs. So it's a question that I just would be interested in other people's ideas of answers to that problem.
Kathy, I'm going to let you do this, and I can chime in after you, but are you able to type these comments and discussion in, or do I need to escape my screen?
Yeah, I can do that. Yeah, sorry. Go ahead. Yeah, I'll type it in.
Oh, okay. Okay. I'm going to start, Carl, and I'm not sure there's a perfect solution. I will say that this was a little tough for me too when I first started working with an engineering group in terms of putting these kind of curriculum into, engineering practices into biology, and they were like, no, that's what engineers do. Cheating is good. Not cheating isn't stealing other people's ideas per se, but this idea of sharing ideas and then using them to build and make a better solution. So, yeah, I think that where I've seen teachers use this most successfully is when they encourage students, say they look and they say, hey, Joe's group always comes up with good solutions. And the teacher says, well, yeah, I see that you borrowed an idea from Joe. What could you do to make his idea better? Or, because again, this idea that no solution is going to be a perfect solution. There are always balances between affordances and constraints, and the criteria will probably never be ideally met. The teachers who I see who are most successful at coping with this problem and still getting this idea that engineers do like to share ideas and to build off of each other's ideas are those that have that conversation with their students and say, okay, well, and even help direct them a little bit. Oh, well, where do you think Joe's solution might be lacking? Or, is there a creative way that you can come up with that? Kathy, you got some thoughts on this?
No, and actually, I agree with what you were saying, and then if then the teachers then carry forth with, if they're making presentations to the rest of the group and such forth, asking the students to be very explicit about, oh, that looks just like so-and-so's design. How is that different or similar? And if the kids know that they're going to be called upon to do that, they usually take that one step further.
Carl, did we help a little bit? And does anybody else have anything to add?
It was helpful. It's interesting to me to see how kids become creative, and I feel like it's one of my goals in doing engineering process projects is that they get to be creative. And so while I like the idea of sharing project ideas, I feel like for some students there's I don't have to really work hard here because I'm going to be able to get someone else's idea and use it. And I'm not sure that that serves them well in their future. So I would like to begin to design my projects and my engineering projects specifically to be better in sort of forcing the students, to a wider range of students, to be creative in their in that whole brainstorming and design and looking at constraints on their own without staring across the room.
Right.
Yeah.
And actually, it's in the biology project that we're doing, that was one of the things we tried to do last summer, was to come up with multiple projects that could be year-long classroom projects that the kids could actually continually go back for, right? So that you would actually have a handful of like 5 or 6 per class, let's say, that you could give these design challenges out to the kids. So there wasn't just one, there was multiple ones. So therefore you can't look, right? At least not in that section. Because I can't imagine having to do 5 for like 4 sections. That would be a lot of designs that you would have to come up with. But yeah, so if they all have different designs, at least they can't look in their own section at other kids.
And I'm going to bridge between Carl and Lynn's comment, which Lynn has assessment thoughts, and so we can talk a little bit more about that, but I want to bridge a little bit. And the other thing I was thinking as you were talking, Carl, was to make creativity as part of the rubric of assessment, so that it is part of the criteria that you are evaluating students on, or that their peers are evaluating them on, because it can be very successful to have peers evaluate each other's solutions, and making creativity or originality be part of that might spur students a little bit to not do that, and having that brainstorming bit be as private as you can. The whiteboards could be down on the desk, maybe might help, because yes, you will share out later. There has to be sharing later, otherwise students really get a little stuck. But there are the initial brainstorming with the group, because any idea flies. Every group, no matter the ability of the students, should be able to come up with something or several ideas that are productive.
One thing I'd like to add too is I'm usually like collaboration over competition, but having a competition makes the students more protective of their ideas, more clustered around them so others can't see what they're trying to do, and that can help sometimes to overcome the problems Carl's been talking about.
So Megan has 2 things out there, and one is assessment thoughts, and one is about a thought about having explicit instruction on each aspect of the engineering framework with standards-based feedback and assessment might be effective. I'm going to go in reverse order and just do my thoughts, and then I'm going to ask Kathy to bounce off my ideas about that, and then also move on to assessment thoughts. So I am very much imbued in the modeling instruction pedagogical framework of having students use science practices as they do things and becoming familiar with them. And when I do engineering, I kind of like to do it the same way too. And I'm not saying that I'm talking from a very personal point of view here. Um, and and so that is probably the way I would go, is that give students some structure, like when I'm having students, for example, evaluate data as a scientific practice, I give them a T-chart, so that, and they do observations first, and then they do evidence and conclusions. And so I give them some structure, but they are participating in the scientific practice without me having told them explicitly what it was. And similarly with the engineering practices, I give them some guidance, but then I allow them to participate in that practice. And we may have a discussion afterwards about what worked well and what didn't, and what you would do next time, particularly if you were using this throughout a whole year. But that's just my where I'm coming from, I guess. So Kathy, did you want to speak to that a little more, and also about assessment thoughts?
No, actually, no. You basically said everything I would have said. Yeah.
Yeah, we're very much imbued in that pedagogical framework.
Yeah.
I think. And what about assessment?
Well, assessment is something that's very, I think, individual to whatever teachers feel comfortable doing. And I with engineering projects, I always used rubrics and peer-to-peer grading, and also, and then myself as using a rubric, looking at those types of the framework, the engineering framework, those engineering practices that they were using, and how well did they actually discuss that and talk about that. I don't know.
And I think an
yeah,
important part of the assessment, I think, is the working in teams and having some kind of feedback to each other, and also about teamwork, and having some kind of way to help them learn how to do that.
Does anybody does anyone else have any comments about assessment and how they might think about looking at assessment for these engineering type of projects?
Okay. Are there any other questions or comments?
For assessment, this is Carl again. I like to have it so that when they're doing an engineering project, that there's some, I suppose, constraint in that they have to meet some objective. Like if they're building a spaghetti bridge that's a meter long, it has to hold a 2 kilogram weight or something like that. I usually have some constraint, and then that their grade is based on their ability to make sense of how they constructed this thing to do that. So I struggle with assessments on these things because there's a wide range of solutions, and mostly they're solutions I'm not prepared for, because the students are smart enough that they try to figure out the easiest way to solve the problem. And so I don't do very well with, whenever I come up with the rubric, it seems like the students break the rubric with my own constraints that I give them. So I've struggled with this, and mind you, I'm new at it. So
No, I agree. No, I've always struggled with it.
Yeah. It's a little tough because you have the criteria, that you have, so it has to meet criteria, right? You're exactly right. So that's part of it. And then there are these resources and constraints, and then there's the affordances of the solution and the constraints of the solution, and allowing multiple pathways. And I think that in part, it has to be about the argument they make, that their solution is a good solution, and that it maximizes the resources, minimizes the effects of the constraints, that, and their daily logs. I like that idea. So it's about what they've done up to that point, and I think, and their final presentation and the argument that they are making as much as anything. So when they, and their creativity, and it's very vague, and it's a very hard thing to assess in some ways. I like Megan's example of trying to figure out whether students have mastered an engineering practice, which is a little different than I think what we were talking about. Thank you, Megan, for steering us in a different direction, which is about how to assess projects. And she said, if I want to think about how to figure out have they mastered the practice of analyzing constraints, she said in the chat that they should be able to look at novel examples. And I think that's also a good idea, Megan. You can, assess their ability to apply the practices to novel situations. And that could be a good way to go. And that allows for an individual piece as well, which is nice.
Right, and Lynn had mentioned too about daily logs also. So if so that's an interesting way to tack upon the idea of what are you showing is happening in your thoughts and process along the way. And that was in the chat. Okay, well, I think we've held y'all long enough. 8:17. I'm sure we have other things we need to do. But if you'd forward through the slides real quick. Oh, you already did. Never mind. Sorry. It's in front of yours. So the references are there, and if you want any of those references or anything, please feel free to email me, and I'll be glad to help you with that. And thank you very much for staying until 8:18.
Yes, thank you, and thank you for contributing and having a discussion with us. We like that as much as anything else.
Yes.